Hello, folks. Thank you for sticking around for the last session on a Thursday. Well, we have more sessions tomorrow as well, so hopefully you'll be in to see some of them as well. I'm Stephen Jones, as my hype man Fred was telling you. And I'm one of the CUDA architects, and so I spend basically all my time thinking about CUDA. I've been working with CUDA since 2008. And I've been doing this series of talks, over the last 4 or 5 years, I think, on how to write CUDA programs, how CUDA programming works. I'm never going to teach you in 45 minutes how to do parallel programming, right? That's not something that you should bother trying to do in this kind of time frame. What I try and do is sort of set a mental model about how the GPU works, and have you think about how I think about how it works. A lot of the way that we build CUDA is, as the hardware architects develop new things, we think about how can this be portrayed in a meaningful way in a programming language that's intuitive and that makes sense to people. And so sort of sharing what's in my head in terms of how I think things work will hopefully help you get a sense of the way that CUDA works well. And so this particular one's about parallel programming. It's a particularly hard topic. I'm going to start easy. It will get a little bit technical. But really, fundamentally, the truth is that parallel programming is hard. And so fundamentally, don't do it. It's way easier not to do it. You really don't need to do it very much. As a member of NVIDIA, I get access to Jensen's lovely keynote slides. This is from one of his keynotes. All those Christmas tree things are these dependencies that he has, or that his artists drew, of all the different packages we've got. And every one of those green dots is one of the hundreds and hundreds and hundreds of packages that NVIDIA has. And really, parallel programming is only right there. And none of the others really need parallel programming at all. And so you really don't need to do any parallel programming. And so because we're all programmers and we're all fundamentally lazy, and for every 10 lines of code you write, you get a bug, you shouldn't do parallel programming. But CUDA builds this entire stack of things to help you not do parallel programming. Right? The secret of CUDA, I put this on the top of the slide today because it was something I was saying to someone just the other day. The secret of CUDA is that it's not just one thing. It's all of these things. Right? There's these levels of abstraction which break down who's responsible for doing what in the application. And of all of these layers, and there's way more stuff at the top than at the bottom. There's hundreds of SDKs and only a handful of compilers. There's really only one layer where parallel programming is actually needed, and that's when you're writing a GPU kernel. And we'll talk a bit about that, but largely we're not going to talk about that. We're going to talk about how to avoid writing a GPU kernel. There's a little bit of parallelism that you need, sort of a little bit higher up the device side, but it's a different kind of parallelism. I'll get to that as well. That's much more interesting because it's much easier to do. But largely speaking, you can go a long way without any parallel programming at all, and that's probably the first thing to do. And I wrote this, I kind of liked the subtitle as well. There's actually a lot less parallelism to CUDA than you think. So I thought, I'll just make a slide of CUDA. A lot less parallel programming than you might think. And that's good because it's hard, right? And you should try and avoid it. And so to help you avoid it, CUDA has built this giant array of different things. I had this slide in a previous talk a couple of days ago. And this is obviously just a tiny fraction of the things that are GPU-enabled. But the point is all of these things exist, right? It's this little corner of the CUDA platform stack. But they all exist because you're much better off at the top than you are at the bottom, right? That line that I drew, the no parallel programming needed, is the vast majority of these things. And it's very productive to use it. Parallel programming is hard and annoying and difficult to debug. And calling someone's framework, which just does it magically for you, and they've done the debugging problem for you, is much, much better, right? And somewhere down below is dragons, and it's very complicated, and you don't really want to go there. And we'll touch on it. But largely speaking, you don't have to do much, because I made up some pie charts that I just completely invented. But largely, if you think about programming, right, you've got a bunch of boring stuff that we all have to do, and AI code assistants are hopefully going to change all of that for us. And then I had one write some unit tests for me the other day, and it actually came out with sensible, reasonable unit tests. And so I'm hopeful that the boring stuff, like config file management and those types of things, that can all be farmed off pretty soon, not to interns. Apologies to anyone who was once my intern, but to actually coding bots instead and give the interns something more interesting to do. Right, so the code that you actually have to think about is probably less than half. And of that of that less than half the code, the majority of it is sort of the stuff that your program needs to do, right? Memory management and communication stuff and sockets and all the rest of it. And the actual stuff that could be parallelized is just a fraction of that. And of the stuff that could be parallelized, the overwhelming majority of it is probably algorithms that someone has already done for you. And so really, if you, honestly, if even 1% of your code is actually stuff you need to write parallel programming for, then you mostly should be paying attention to the other 99%. That 1% is still important, but it's not where the bulk of what you get done and the performance gains you're going to get and the productivity gains you're going to get are going to, then that's not where they're going to live. Right? So a place that you often start, excuse me, a place that you often start is at the very top, right? These frameworks, and I've thrown a few different things on the screen here, some AI frameworks, some graphics ones, some computational physics ones, and what they do is they take you into their embrace and they help you build an application, usually in a very specific domain, whether you're making AI networks with PyTorch or whether you're doing molecular dynamics with something like LAMPS, or graphics effects with Houdini. All of these things, they put you in the shell, they provide you with ways to program much more efficiently, and you get way more done. They're very productive. They are much easier to think about. They almost never show you parallel programming, right? And they're all GPU accelerated. And there's, at this point, hundreds and hundreds of things are GPU accelerated, so you actually have a lot of choice, which is fantastic. If the framework doesn't quite cut it for you because you're making your own bespoke application in some way, then almost certainly the majority of what you need is going to be available in CUDA's math libraries. This is some of the low-level libraries. There's a whole array and stack of hundreds and hundreds of these things. The low-level libraries are really the core functionality, the building blocks, if you like, that you'll build things with. So cuBLAS is linear algebra, cuFFT is Fourier transforms, random numbers, different operations. There's a whole family of these different things. But the math libraries are your mainstay, right? These libraries have been tuned by NVIDIA ninjas over years. You would spend years to write a program that came close to what these things will do. And why would you? You've got better thing to do with your years of work. And if you do write a program that beats these, you should definitely talk to me because I will hire you. Because the people writing these, my first job in CUDA actually was at NVIDIA was writing the FFT library. And the people who do it now are way better than me. Because they did a great job on it. So use the libraries, and I say this every time, because I talk a lot about programming CUDA, and the answer is, these are the things that you should never even try and match. But if you have to go somewhere the libraries don't go, because not everything is a pre-baked linear algebra function in cuBLAS, there are, of course, programming languages which still is not CUDA, and still is not a thing that you have to get to. I mean, some of it's CUDA, but these are things from the CPU. When you string your operations together, these languages, these packages, these constructs allow you to formulate parallel code without ever having to invoke a GPU compiler. Right? So I'm giving you all the reasons and ways that you're not going to be doing any CUDA programming, because I think parallel programming is hard. It's a big waste of your time unless you really, really have to do it. Right? So speaking of time, here's actually a chart that I used to show the interns. You kind of think ideally that you're going to be, I put in some effort and it'll get better. I do 2 weeks, it's twice as good as 1 week, and I get to the end, and then you go and you look up PyTorch or something like that, and you go, oh, it's going to be amazing. It's going to give me peak performance instantly with no effort, right? When the real world is a little bit, more realistic, is you're going to kind of gradually improve, and then you'll go through a phase of goodness, and then it'll kind of curve off. But the truth of the matter is actually much messier than that, and we spend a lot of our time frustrated and banging our head against the table, and in fact, the very end thing that you end up doing is hiring an intern, because the interns are just so brilliant about these things. And I see some of my old interns laughing in the audience. And but this is really our experience programming, right? But back to the slightly more realistic curve. The goal of all of us, and the reason I start telling you about parallel programming by telling you about not parallel programming, is because what you want is to shift this curve to the left. Right? You want results fast. You want good enough results with less effort. And you really don't want to waste your time on that long tail at the end of just tuning that. It's the 80-20 rule, right? It's the last 20%. It takes 80% of the effort. And so, you can draw these curves of these different types of things. The frameworks, you get, it's not zero time to success, but it ramps up pretty quickly. It maybe doesn't get to the same peak as some ninja-tuned NVIDIA library, and you can probably hand code your kernels if you're going to get a job from me. You can hand code your kernels to be even better than that. But largely, you want to be on the left-hand side of this picture, except for the 1 or 2 cases which really matter. But I promised to tell you how to write a CUDA program. So, well, first you write it by not writing CUDA, but I will tell you about some of the CUDA as well. So, and I realize I should keep an eye on time, because I do have 98 slides today. So this is like the OG example of CUDA. This is the very, very first example that Ian Buck wrote up to tell people how the hell does CUDA work, right? It's implementing the single precision AX plus Y routine. It has many properties. It's a routine that's very important in matrix multiplication. It's been in every library for the longest time, and it's the most useless benchmark for benchmarking any machine ever. And when anyone shows you performance for this, you immediately ignore them, because it's purely just a memory benchmark. But what you do is you have a function, and it takes a couple of floating point arrays x and y, and then they multiply x by a and add it to y, and that's the result. And in a normal CPU program, these things serially go through a big for loop and calculate the whole array. This is how the CPU has always worked. Now, for the GPU, the way CUDA would change this is to say, instead of that for loop, and let's say I've got 1 million elements down there on the left-hand side. So 1 million elements of CUDA, what you do is you launch 1 million threads. And so instead of having a sequential for loop, you have a parallel, what we call a grid launch. The grid's launched in 2 different dimensions. I'll tell you a bit about that in a moment, and I think probably many of you know this as well. As I said, we're going to start easy and get harder. But what this does is launch 1,000 blocks with 1,000 threads, and the result is that all of those 1,000 threads instantaneously calculate things, and you're much better off. And this is the essence of where GPU performance comes from, right? It's this massive parallelism. And the way that it actually runs, the reason there's 2 numbers, like 2,000s instead of just 1 million, is because the GPU itself, like a multi-core CPU or like pretty much any processing device, it has lots of different processor cores. We call them streaming multiprocessors. And so this universe of 1 million threads that I need actually gets broken up into what we call thread blocks. And the thread blocks then get mapped onto a GPU. I've got a picture of a very old GPU from 2012 here, because we only had 15 SMs back then. But largely what happens, each one of these yellow things is an SM, a streaming multiprocessor for the GPU. And what happens is these different blocks land running on these different SMs, which is the processing cores. Each SM itself has 2,000 threads inside of it. And so by breaking my work up into these blocks, just like you would on a multi-core CPU, then you're able to exploit the natural parallelism built into the hardware, right? And because 1,024 threads are allowed in the block, you can actually fit 2 blocks of my 1024 size program on a single SM. And so my 15 SMs could run 30 blocks of my program here. Now, I use this old GPU because even though it's got 15 SMs, and that's way less than the 1,024 blocks we've got, when I look at a more modern GPU, Hopper, I didn't have a picture like this for Blackwell, otherwise I'd have showed you Blackwell. Hopper has 132 SMs. That's still way fewer than 1,000 blocks. So a key element, and if you've seen any of these talks before, I always point this out a lot, a key element of the GPU programming is oversubscription. You want to give the GPU more stuff than it knows what to do with, right? More stuff than it will fit on it at any given time. And that's because the way that the GPU runs these things is it will fill the SMs with all the blocks that it can find. And then as one block leaves, another block enters. And so the amount of time that your GPU is idle is very small. There's 132 SMs on this Hopper device. And that means that when one leaves, less than 1% of my GPU falls idle. And so by having a deep, deep, deep pipeline of many of these blocks, the total, instead of firing up a lot of threads and shutting them down, and firing up a lot of threads and shutting them down, where the whole GPU would go dark at a high frequency, it's just small pieces. And this makes a much more smooth and clean throughput. It's also a great way to scale, right? So we had 15 SMs at 10 years before Hopper on Kepler, and with effectively 10 times the number of SMs, or 9 times the number of SMs, Hopper naturally just instantly runs 9 times more stuff. And that's because I have a lot of blocks. If I only had a few blocks, it would never have filled Hopper. But by oversubscribing my machine, I scale pretty nicely over 10 years. Excuse me. So a subtle point, though, I showed you, here's a million bits of data. I'm going to launch a million threads to process them. I kind of correlated threads with data there, and that's actually not true. I lied to you about that, right? We broke up our million threads into 1,024 blocks of 1,024 threads each, right? That's what the arrows were showing. But because threads and data are not the same thing, right? We ended up with a million threads for our million elements of data, but my Hopper device only has 250,000 threads. 250,000 threads is a lot of threads. It's a lot more than your CPU would have, but it's still way fewer than the total number of threads that I need, hence the streaming of those blocks. But even though I can stream the blocks through, this isn't the only way to have divided my work. I don't have to do one-to-one. In fact, there are real benefits to not doing one-to-one, right? The fact that this requires a million threads and doing one element per thread, you can see it's structured in my program there. That indexing thing that I've highlighted right there is where I say, what is my thread ID? I'm going to index my data according to my thread ID. So I've launched a million threads. If I'm numbered 1,000, I'm going to get data element 1,000. I didn't have to do a one-to-one mapping. I could have said, let's do 4. Let's multiply my index by 4. So each thread is going to take 4 elements of data. And then I'll do I plus 1, I plus 2, and I plus 3. This is just very basic CUDA C++ code. And now each thread is doing multiple things. I now have a quarter the number. Well, first, actually, I've got to be a little bit careful because if my threads don't divide perfectly, I have to have a little if case in there to make sure that I haven't read out of bounds. And then finally, I have to update my launch. So instead of launching 1,024 blocks, I launch 1/4 of that because I'm now doing 4 elements per thread. So I've got to do a few adjustments. It doesn't happen automatically. It's actually something very, very difficult for a compiler to do for you. So these are the kind of transforms you have to think about when you're designing your code up front. And the result is that now I can fit almost perfectly on the machine. There are a lot of benefits to doing this. And the benefits are, of course, that not only am I fitting on the machine and launching fewer blocks with a less overhead, but I'm actually batching my memory loads, and I've reduced the amount of jitter, and there's a whole bunch of reasons why on my laptop this runs twice as fast. Right? And there's a lot more you can do in what looks like a very simple kernel to actually boost this way, way, way more. I've got an example from my colleague Mark Harris, who many years ago did something about reductions, and I'll show you something of that later, where he demonstrated sequences of optimizations that you can make. And I'm not going to go through those types of things here because that's already out in a paper and a presentation. But the point that I want to point out here is that the way that we've designed the GPU is built with this exact thing in mind. The idea that you've got lots of blocks, more blocks than you can fit, more threads than you can possibly fit. We give you a lot of choices about how to slice and dice them. As each architecture evolves, and as Moore's law compresses the transistors to be smaller, we can fit more SMs onto a piece of silicon. But notice, while this SM count goes up, which is the core count, the number of threads per SM does not go up. And the reason the number of threads per SM does not go up is because to change the width of my program is a significant structural change to my program. You saw even just changing from 1 element per thread to 4 elements per thread involved touching my program in 3 different places. So while we could just say, well, build one giant SM across the whole machine, that's actually bad in terms of future-proofing because then the next machine getting bigger forces you to go back and change your code all over the place. And we care a lot about the fact that your old code runs on new hardware. But not only that, the fact that if you had a large number of threads, every time you need to synchronize your threads, you've now got to communicate all across the GPU. There's very good reasons to keep things to a reasonable size. And 2,000 threads for the last 15 or 13 years has been the choice that we have made. So locking in that, increasing the SM count, streaming with too many blocks, that's really the way that GPU programming scales. And so as you think about your parallel programming, you're trying to fit inside these bounding boxes of a large number of independent blocks with a fixed number of threads. And so now we get to the dragons, right? Underneath these dragons, I pointed out before, there's an area of parallel programming, the kernel authoring area, and we're going to start there. We'll go a little bit further up over time. But parallel programming is needed there, and I've just been showing you aspects of even a very simple x plus y program, there are subtleties to it which could make a factor of 2 in performance very easily. And when you think about how work runs on the GPU, I showed this slide last year, and people complained at me because they said there's more than 2 types of parallelism. And there's many nuances to types of parallelism, but fundamentally, the way I think of these things is I've either got independent programs. It could be the same program running in 2 different places, but they're totally independent programs not interacting with each other. Or I've got one program working on lots of data doing the same operation across lots of data. That's task parallelism versus data parallelism. And everything else, whether you've got model parallelism, pipeline parallelism, weights parallelism, all the different parallelisms that people write papers about and publish, they all really boil down to these 2 choices. And the thing about the GPU is that CUDA is both, right? We've broken our data up into independent blocks of work. And that is task parallelism. Even if I'm running the same program on all of them, the program is at a different place. Maybe the instance of the program is different because there's a block ID for everything. These things run really wholly separately. If they need to communicate data, then they have to. There's a whole different talk I could give about parallel data structures and atomics. But largely speaking, I've broken my program into the independent blocks so they can make independent forward progress and run in parallel. Within a block, my 2,048 threads on my SM, it's actually a maximum of 1024 threads in a block. That is the data parallelism. That is where the kind of code I was showing you before comes in. And so this fact that we've got both of these things to make the GPU run efficiently has interesting implications, I think, for how a CUDA program works. Right? So we'll start with the data parallelism because that's the hard stuff. Right? When I said parallel programming is hard, this is the stuff that I mean. And this is something, if you've ever sat in a computer science course, something like a reduction, which is this operator that I'm showing you right here, is one of the first things you see because it has a quintessential property of parallel programming that's incredibly powerful. Right, so here's my serial code for my reduction. Looks a lot like my AX plus Y. And what I'm doing is I'm summing all the pieces together, and in this picture I've got 64 boxes, and so it's going to take me 64 steps. Now, if I have a multi-core CPU, I can hand this off to different cores. A 4-core CPU is today you have many more than that. But if I had a 4-core CPU, I could do it serially in 4 different chunks, and I'd go 4 times the speed approximately with a final addition at the end. And if I had a 16-core CPU, right, I could then do even more. I can keep breaking it up apart. Interestingly, when you run into something like this, you get to this point where you've broken it apart so much that the second step of adding it all together cancels out some of the benefit you got from going parallel. So you do have to think about how the interaction between the separate pieces adds up as well as the optimization you've got on the individual parallel pieces that you're doing. And this is classic stuff for a divide and conquer kind of algorithm, right? So I'm dividing even more, I conquer it faster. To overcome that final addition, I can divide and conquer twice. I can keep dividing, and I can keep on conquering, right? And this divide and conquer approach is really the essence of a lot of these. There's a set of core fundamental parallel algorithms, and reduction is one of them, where by doing this division and conquer, this pairwise, or it can be more than pairwise, but this repeated recursive sequence of operations to reduce things down to a single result, that gives you what, instead of being a linear amount of time on a CPU, is a logarithmic amount of time. And this is a hugely important thing for programming in general, because the time order of my algorithm says to me how, as I get more data, as I get more work to do, how fast can I solve it? Right, so matrix multiplication scales as the square of the number of things you're trying to solve. So as your matrices gets bigger, it becomes unsolvable. Problems where doubling the amount of work only gives me 40% more compute to do. That's really interesting because now I have a superlinear speed up on my, or a sublinear slowdown, I guess, on my work. So this is the essence of parallel algorithms. And there are several of these really core building blocks, basic building blocks of parallelism, things like sorting and prefix sum. Map is a slightly different beast, but again, it's applying functions in parallel across a whole array. These are the things which, if you look up a parallel programming book, they spend a lot of time on each of these. Because when you write a parallel program, these are the functions that you have in your head, the toolbox that you have as a programmer, to take your data and approach it in a parallel way. The more you can convert the sequence of operations to these types of operators, the more you're getting out of your parallel program because it scales logarithmically instead of linearly. You really lean into the threads. Now, another property of these is the degree of parallelism that I can bring to bear has major implications. The more threads I've got, the wider a thing I can do a reduction for. On the left-hand side is my I've got enough threads for everything, and that works in logarithmic efficiency. On the right-hand side, my quad-core CPU, it doesn't really quite scale the same way. So once I run out of threads, I end up effectively serializing my chunks of parallelism again. And this is why these algorithms are incredibly beneficial on the GPU, because I've got 250,000 threads. I've got a lot of threads I can bring to bear on these algorithms, and so they become incredibly powerful. So in terms of this reduction, even though the code is relatively simple, I got this code from Mark Harris's paper, a basic parallel reduction is just loading up some data, doing pairwise additions to them. He did something slightly smart and used shared memory. I'm not going to deep dive into that. There's plenty of things telling you online telling you how to do reductions. But the point is the code is relatively small, relatively compact, and I can enact this parallel reduction very efficiently on the GPU. But in the same way that I could double my performance by simply reading 4 values per thread in my previous example, I can do even better with more complex things like reductions. But suddenly my code is templates and complicated switch statements and all sorts of weird synchronizations. There's all these optimizations that happen, and his paper points out that if you do this stuff that's too small of a font for you really to read on the right-hand side, let alone time for you to work through it, there's a factor of 30 speed-up difference between the basic and the ninja level of work. And he has a few other points like along the way. He does this, I think, in 7 steps. It's from like 2009 or 10 or something, that paper. It's a great paper just because it so clearly points out, here are the steps you can take to go from 1x to 30x. And so if you're a ninja and you can come up with this and you understand enough about the GPU, and you've watched all my previous talks, so you've learned about it or whatever, but if you can do this for reduction, you can get a long way. But just imagine doing that for every single one of these operators. There's people write whole PhDs on ways of doing parallel sorting. And there's just, you would go crazy trying to optimize each one of these detailed pieces so you can put them all together to solve an algorithm that you've got, right? I actually used to ask in interviews, I used to ask people to write me an algorithm to find the unique elements in an array. I stopped asking it because it's kind of unfair, because it turns out it's really hard. It's not, if you understand your parallel operators, you can just do it in a sequence of about 5 or 6 steps. But people would just tie themselves in knots and get very upset, so I stopped asking it. But anyway, the point being, though, you don't need to write these things yourself, right? Because data parallel programming is even harder than any other kind of parallel programming. Because you've got to think of all these things, and so you shouldn't do that either. And the good news of that is someone's already done it for you. In the same way that we have these math libraries for doing Fourier transforms for you, and no one in their right mind should ever write a Fourier transform ever again, except Lukasz. We've got these libraries for kernel functions. These are included and put into your kernel, so you can invoke a sort, or a reduction, or a prefix sum operator, or all histograms, or all these other things that are available. This cub library, which is part of the CUDA C++ cooperative CCCL library, and its Pythonic cousin, I guess, CUDA cooperative, which is the exact same thing, but in Python for writing Python kernels for, because this year we've really gone big on putting Python up and down the entire stack. Cub offers all of these operations, and it doesn't just offer them in terms of a block wide, which is what we've been talking about here, but even sub-block, things called warps or the whole device. It's very, very flexible. Again, written by ninjas who know far more about that stuff than I know or than you know. And why would you write that again? It's in that 1% thing. Like, don't do the other 99%. Just work on the stuff that you need. And these are basic building blocks, right? You can literally build any parallel program with these foundational things. But don't go and build an FFT with them anyway, because a lot of the math library functions for these 4 libraries, the linear algebra library, the Fourier transform library, random number generation, and matrix factorizations, they are like, some of their functions are available also for calling inside your program. And so That means that if you needed to produce random numbers or you needed to multiply some vectors together or something, rather than writing it yourself and going through all of that code, like disgusting and terrible and difficult to debug code that I was showing you, just go and call one of these library functions. We put a lot of effort into making sure that at all these different levels of abstraction, whether you're writing the low-level cub operators, invoking the libraries directly, or just launching something as a giant grid across the whole machine, there's something there to try and avoid you having to do any parallel programming. Now, sometimes you can't fully avoid it, right? Because on the right-hand side there are these things I've been talking about, this task parallelism. If a CUDA block is a task parallel construct, a unique program, one instance of a program running many times across the machine, these functions which take over my block and take over the threads in my block are the things, they're operating on that right-hand side, the device library section, the task parallelism side of things. But it's still a library. If I need some weird linear algebra thing that cuBLAS doesn't have, some matrix solve that hasn't existed before, some strange image processing filter that I have to write for myself, I am still going to have to go and write that code on the left-hand side, the light green arrow. And you can mix and match these things. It's very important for whenever we build anything in CUDA that you can mix and match them. But really fundamentally, while libraries can never cover everything, right? I need that custom code. And so, can we get the best of both worlds? And this is something which we've been working on for quite some time to try and bridge that gap between pre-baked stuff that the ninjas have written for you and getting your hands really down and dirty with crazy warp-level template programming. And I think we can do something. We can get you task parallel at the kernel authoring level as well, right? I've been talking really about this hierarchy of programming models. If you saw me talk about this a couple of days ago in the talk about what we're doing on CUDA, I showed this same picture. You've got these three sort of levels of parallelism. You've got bulk parallelism on the right-hand side. Sorry, the left-hand side. It's backwards. You've got bulk parallelism on the left-hand side, which is how PyTorch works, or anything generally works. You've got on the other side, on the far right-hand side, you've got the low-level thread stuff we've been talking about. But in the middle is this task parallel programming, which is much more accessible, much easier to debug, much easier to think about if you can still do useful things with it. That's where the cub library and the math, device-enabled math libraries exist. And so we built a programming model, or I guess we are in the process of building a programming model because you never finish building one of these things, that we call cuTile. And I showed this slide a couple of days ago as well. This is tile programming for CUDA, and I'll tell you exactly what I mean by tile in a moment. Right, this is that block-wide task parallel operation where you're not having to go all the way down and dirty and get into data parallel thread management, but you can still write very general programs so if the libraries aren't giving you what you need, you have access to these things. Right, the granularity is an array or a tensor. I do, tensor A plus tensor B equals tensor C, instead of having to explode it into individual elements. Because it's shockingly common that many of the programs we write, well, not very shocking at all, is that many of the programs we write do have pretty regular chunks of data, image processing, or linear algebra and matrix multiplication, or even the unique deduplication work that an interview question I used to ask and no longer do. Right? But the other benefit of tensor programming is, of course, we have a lot of tensor hardware inside the chip for accelerating some of these expensive and difficult n-squared operations. And I can map tensors, or I can get a compiler to map tensors, relatively easy onto things like tensor cores. And so the power that you can get in principle, if you can express your program as these data parallel tensors, you've simplified your program a lot, but you still have a general programming model. I think this is exactly the gap that I was looking to fill. So let's talk about tiling data. Because if I've got a tile programming model, I should explain to you what I mean by tile. Right? And the same kind of granularity decisions have to be made that we made beforehand, earlier on for my AX plus Y example, right? In my AX plus Y example, I had this giant array of data, and I split it into a bunch of blocks, and then I figured out that actually I can do a lot better if I'm doing multiple elements per thread instead of one element per thread, because that's generally true on the way, from the way that the GPU works. And so this 1D simple example, this can also apply in a similar way to how I tile my data, right? Remember, data and threads are not the same thing. Or in this case, tiles and blocks are not the same thing. I can explode my problem into an 8x8 grid of tiles, sized perfectly to fit inside my cache or my shared memory or something like that. And I can issue one tile per block, just like I previously issued one element per thread. It's probably not the best, but I can do it, and it's nice and easy. But I could group this in all sorts of different ways. I could have a block per row. I could do 8 tiles per block, right? So I've got a 1x8 grid now, and I'm only launching 8 blocks. Or I could have a 2x8 and break it into different pieces. Now I've got 16 blocks. Or I could have them square. I could have them long. I can do all sorts of different things in the ways that I choose to break my program down. One of the questions I got when I was talking about this on Tuesday, someone said, why don't you just deal with the whole grid of data? And the answer is, because the choice that I make, right, the choice of these different shapes and things that I've got here, do I do it as separate pieces, as whole rows, as columns, as squares? That choice depends on what I'm doing. If I'm processing strings, I probably want long horizontal pieces. If I'm processing sparse data, I probably want columns. If I'm processing images or something, I probably want square shapes like this, right? Because the way that you break it down is a function of what your data is about and the processing that you're going to do on it. And there is no way that I, at the level of a CUDA compiler, can possibly know anything about your application. So I'm not going to try, because I'll not do as good a job as you. So I'm going to ask you to do the first step, the task creation step of breaking your data down, and then figuring out how to map it for like 4 tiles to a block, or 2 tiles to a block, or 1 tile to a block, or whatever you want to do. But the key part of this programming model is that you're launching a grid of blocks to process tiles, just like in regular thread programming, you launch a grid of blocks to process threads. These are tile blocks instead of thread blocks, if you like. But because we are in task parallel mode, because we are in array-based mode, your program really only has 1 thread. Or it looks like it has 1 thread, because vector A plus vector B equals vector C doesn't take lots of threads to do. Under the cover, a compiler is going to sit there and understand something about your data and understand how that mapping is going to apply. And it's going to make all those great decisions about crazy stuff and get a factor 30 speed up that none of us really understand and don't want to learn enough about the GPU to understand. You should not be spending your time on that if you don't have to, right? Parallel programming is hard. Don't do it unless you have to. Here you're doing some parallel programming. You're breaking your thing down into independent pieces. You do have to think about that. But after that, you're saying, no, I'm just going to write at the tile level. I'm going to program at the task level. And it's going to take this for me. And it's then going to figure out the mapping onto different pieces of hardware with different shared memories. And maybe one hardware wants 4 elements per thread, and another one wants 8 elements per thread, and the compiler knows all that. And I don't even remember what the proper balance is for all the different GPUs. We've got so many generations of GPUs over the time I've been here. Right, so really, this cuTile programming, we've extended CUDA with the thread CUDA that maybe you're familiar with, I'm certainly familiar with, but thread CUDA I've told you a lot about, to this blockwise, tile-based model, which I think bridges the gap between that and the Ninja-tuned libraries that you can invoke, like Cub and like the cuBLAS DX libraries and so on. Right? Tile parallel programming feels more like task programming, but it's down at that kernel authoring layer. And because you've got regular piece of data, regular structured data, right? Because of that, the compiler understands how it needs to traverse this data, how it needs to do the mapping. By communicating enough extra information that this is a dense block of data, and here are the dimensions of it, you can this is like a brand new, not yet well optimized compiler, and it is coming within 10% of a cuDNN program that's been tuned by ninjas for 10 years. Right, which is no aspersions on cuDNN. It's literally the state of the art. It's like, for us, it's like, how close are we to cuDNN is always our question if you're doing something like an inference network like this, right? Which is, this is Llama 3 inference. It's a Llama 8B. It's not huge. But the point is that you can take something like this with really all the hard decision making being made by the compiler, and the compiler can understand enough about what you are doing to get within 10% of the state of the art. And I hope, as we work on this compiler over the next few years, that we'll add more optimizations and more intelligence and asymptotically approach what that is going to be. Right? Not everything is data parallel. Not everything is a nice regular bulk array. And so they're not going to take that away from you. You can write tile things in tile, array things in tileman. You can have do your decompression engines and hash tables in thread mode. Like, pick and choose what you want to do. In the same way, you can add libraries from any way you want and put things in frameworks. Don't do any more work than you have to. But every now and then, you're going to have to do some thread kernels, and that's fine. But the point is, I'm trying, like, if that 1% gets to sort of 0.1%, then I think I'm winning. Because I think that you are being more productive, and you're getting much better results. And honestly, like, the amount of time it would take me to sit down and write a kernel after 15 years of CUDA experience or more, and write a kernel that would compete with CUDA to within 10%, it would take me months. And this took us a couple of weeks. And it's only the beginning, too. So really, the story of all of these things is to have your cake and to eat it, right? It's all of the above. We've managed, I think, to first build enough stuff that implicit parallelism above the line there, that most of your code, you never ever have to write a single line of CUDA. And I hope we can continue to do that, and you can write less and less CUDA. As one of the architects of CUDA, I hope that I can help you write less CUDA, right? And every now and then you have to, but we've got a whole bunch of libraries to help you with it. And when you have to get down and dirty and the libraries don't cover it, we've now got something else on top of that, which simplifies that data parallel, really difficult parallelism that you should avoid at all costs. Failing that, yes, you can drop down into the very lowest level of stuff, but the more I can make that light green thinner and thinner and thinner, the more you're going to be able to get more stuff done with GPU, more interesting algorithms created. And we're just going to keep on building more and more pieces which build on top of that light green, just so that the secret sauce is kept to an absolute minimum. Because then we're more productive, we get the performance we want, we're more effective. We've shifted that curve to the left that I showed you, my sort of imaginary intern curve. And so that's it. I think I've probably way overstepped my time, only by 5 minutes. But thank you all very much for listening.